Section 3.9, Related Rates. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So we are given one rate of change. We are given that the change in volume with respect to time, or dv dt, the derivative of volume, is 100 cubic centimeters. We want to know a different rate. We want to find the rate of change of the radius, dr dt, with respect to time. So we don't know what this is, but we want to find out what it is when the radius is 25. Okay, so for a spherical balloon, the volume of a sphere is V equals 4/3 pi r cubed. So that means that dv dt, which by the chain rule is dv dr times dr dt, is equal to 4 pi r squared times dr dt. Notice that there were no t inside this formula that we have for volume. So when we take the derivative, if we want to get the derivative with respect to t, we have to first go through r, which is a function of t. As a result, we have to use the chain rule. We have to first differentiate with respect to r, get 4 pi r squared, then we have to multiply by the derivative of r with respect to t, which is dr dt. Okay, so now we still want to find out what dr dt is. We know what dv dt is, they gave it to us. So that means that if we solve for dr dt, we can divide by 4 pi r squared on both sides and get that dr dt is equal to 1 over 4 times pi r squared times dv dt. So we also can plug in our values for r and for dv dt at this point. Notice that we could not plug in r equals 25 in our formula for volume over here, because r is a variable. This is kind of like when you want to do the derivative f prime of x. You want to know what f prime of, for example, 2 is. You don't plug in the 2 until after you take the derivative, because x is a variable. So if you want to know the value of a derivative at a specific variable value, you have to first take the derivative. You cannot treat it as a constant when taking the derivative. So we had to leave r as a variable in order to take the derivative, but now that we have it, we can plug in the r value of 25. Remember, they said the diameter was 50, so r of 25 is half of that. Okay, so now we multiply by dv dt, which is 100. We get 1 over 25 pi. So that's roughly 0.0127 centimeters per second, which should make sense because it's a radius. It should be one-dimensional for centimeters, and it's a rate of change, so it should be per second. A ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So let's see if we can draw the situation. Here's the wall, here's the ground, and then here's my 10-foot ladder. So the ladder is 10 feet, that's constant, so I can just put the 10 there immediately. However, it's sliding away from the wall, so this value on the bottom is a variable because it changes depending on time, on what time it is. That'll be how far it's slid away from the wall. Similarly, the height of the ladder against the wall is variable because it's sliding down the entire time. Okay, we are given that it slides away from the wall at a rate of 1 foot per second. So that means that this change, that it's moving away from the wall, is 1. It's getting bigger and bigger and bigger, so we expect it to be a positive value for the rate of change. However, this guy's sliding down, so even though we don't know what it is, we should expect that dy dt is probably negative. So we don't know what this is, that's what we want to look for. So let's find a relationship between x, y, and 10. Well, Pythagorean theorem. X squared plus y squared is 10 squared, 100. So I can do 2x dx dt plus 2y dy dt equal 0 by just taking the derivative everywhere. Notice the derivative of x squared in this case was not just 2x, because we did not take the derivative dy dx, we took the derivative dx dt. We were taking the derivative of x with respect to time. In this case, t is our independent variable, and x is our dependent variable, which is very unusual, because usually we have like a graph with x and y depends on x. In this case, we've got t and x. So when we take the derivative, we have to use the chain rule. We also have another one with t and y. This is also maybe a little bit confusing because notice there's no t in here at all. You don't even see it. But in the context of the problem, our entire thing is moving with respect to time, so there is like a hidden t that you're not seeing, so we still have to use the chain rule and be very careful. Okay, so we subtract 2x dx dt from both sides and divide by 2y because this is what we want to solve for. So we get dy dt is equal to minus x over y times dx dt. Okay, so now we want to plug in because we've taken the derivative. So we want to plug in for x, we want to plug in for y, and we want to plug in for dx dt. We know dx dt is 1, so we could plug in the 1. We know that the bottom of the ladder is 6 feet away at this time, so we can plug in that for x, but we don't know what to plug in for y. So we need to know what y is at the instant when x is 6. So let's use the Pythagorean theorem. If x is 6, that means it's 6 squared plus y squared equals 100. So that means that y squared is equal to 64. So that means that y is 8, because we can't have a negative value for distance. Okay, so now we can plug in. We get that dy dt is equal to negative 6 over 8 times 1. So that's negative 3 over 4 feet per second. So that's how fast the top of the ladder is sliding down the wall when the bottom of the ladder is 6 feet from the wall. And it makes sense, like we said, it's negative because it's going down. A water tank has the shape of an inverted circular cone with base radius 2 meters and height 4 meters. If water is being pumped into the tank at a rate of 2 cubic meters per minute, let's find the rate at which the water level is rising when the water is 3 meters deep. So let's try drawing our water tank. Okay, and we have some water level inside the tank, so that's another cone inside. And it says that the water tank has a base radius of 2 meters. So this is 2, as a height of 4 meters. So if I look at this height, it should be 4 meters. And I want to know the rate at which the water level is rising when the water is 3 meters deep. So I probably want to be able to look at the radius of the water inside the tank. And I'm going to need to know when the water is 3 meters deep, but that's changing, so I should leave that as h to start with, and then plug in the 3 later after I take a derivative. Notice that we can leave 4 and 2 plugged in right from the get-go because the tank shape does not change, it's constant. But this water level keeps moving up or down, depending on if water's being pumped in or whatever. So for us, water is being pumped in, so it's just going to move up and rise, but that water level is variable. So even though we want to know what it is when it's 3 meters deep, we have to first treat it as a variable and then plug in the 3 after we differentiate. So we are given that the change in volume with respect to time is 2 cubic meters per minute. That's the rate at which it's being pumped in. We want to know what the change in height is, dH dt, when h is 3. Okay, so we have a formula for the volume of a cone. It's 1/3 pi r squared h. Now, this is a little bit of a problem though. There's 2 variables in here. If we differentiate, we'll have dv dt, we would have a dr dt, and we'd have a dh dt. We only want to know what dh dt is, and we only have dv dt. We have nothing to do with any kind of r. They didn't give us any dr dt. So that means that we need to somehow eliminate this r so that we're only dealing with the v and the h. So we know that there's a triangle over here, and there's a triangle over here. They're both similar triangles, so they're proportional. So that means that the height of this triangle divided by the height of this triangle is equal to the base of this triangle divided by the base of this triangle. So r divided by h is equal to 2 divided by 4. It's an equivalent proportion to what I said. So if we solve for r, we get that r is equal to h over 2. So now we have v is 1/3 pi. Instead of r, we can write it as h over 2 squared and keep our h. So the volume becomes pi over 12 times h cubed. So now we can differentiate. We won't have to worry about r. We have dv dt equal to pi over 4 times h squared times dh dt. So then we can solve for dh dt. We divide by pi over 4h squared, so we get 4 over pi h squared times dv dt. And now we can plug in because we've taken our derivative. So we get 4 over pi times 3 squared, height was 3, and dv dt was 2. So that equals 8 over 9 pi, which is about 0.28 meters per minute. Car A is traveling west at 50 miles per hour and car B is traveling north at 60 miles per hour. Both are headed for the intersection of 2 roads. At what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection? Almost said meters. So let's draw our intersection. they're going to, let's say, intersect somewhere. I'll call that C. And then we can put A over there. And I can put B over here. So the distance from A to C is, let's say, X. The distance from B to C we can call Y. So that means the distance between A and B we can call Z. And this is a right triangle. Okay, so now we know that car A is traveling west at 50 miles an hour. So that means that X is getting smaller and smaller at a rate of minus 50. So dx dt equals minus 50 miles per hour. Similarly, y is getting smaller and smaller as time goes on. So dy dt is equal to minus 60 miles per hour, because that was the rate for car B. Okay, so we want to know what the change in z is with respect to time, because we want to know the rate at which the cars are approaching each other. So this is what we're looking for, dz dt. Again, we can use Pythagorean theorem. Z squared is x squared plus y squared. We can differentiate. Notice in this case, we don't have the latter being constant. Z is changing in addition to x and y changing, so we can't plug in anything at this point. We have to just differentiate with all three of our different variables. And they all depend on t, so they're all dependent variables. So we get 2x dx dt plus 2y dy dt. Okay, we solve for dz dt by dividing. We get 1 over z, because we can cancel out the 2's, and we get x dx dt plus y dy dt. Okay, so now we have a whole bunch of stuff we want to plug in. We only want to know dz dt. So that means we have to be able to plug in for z, we have to be able to plug in for x, we have to plug in for dx dt, we have to plug in for y, and we have to plug in for dy dt. We know this is minus 50, we know that's minus 60. So we need to know what x, y, and z are. Well, they gave us x is 0.3 at this instant, y is 0.4, so we can use Pythagorean theorem to solve for x. So z squared is 0.3 squared plus 0.4 squared. So that means that z must be 0.5. So now dz dt at this instant is 1 over 0.5 times 0.3 times minus 50 plus 0.4 times minus 60. So that's minus 78 miles per hour. So that's the rate at which z is changing, because z is getting smaller and smaller. The question asks the rate at which the cars are approaching each other. So in the context of the question, the rate at which the cars are approaching each other is a positive value. We just drew it like this so that we could calculate it conveniently. So we should say that the cars are approaching each other at a rate of 78 miles per hour without the negative. A man walks along a straight path at a speed of 4 feet per second. A searchlight is located on the ground 20 feet from the path and is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? Okay, so straight path. Man's walking along. And speed of 4 feet per second, okay. And at what rate? Oh, it's located on the ground 20 feet from the path. Okay, good. So let's go 20 feet away from the path. And then the searchlight is kept focused on the man. I want to know the rate at which the searchlight is rotating. So this searchlight points at the man. And it keeps rotating outward. So this thing keeps moving outward as the man moves. So we're looking for this rate of change of this angle. Let's call that theta. We can let the distance over here be x, so we get a right triangle. So we're told that this man's speed is 4 feet per second, so that means the change over here is 4 feet per second, so dx dt is equal to 4 feet per second. We want to know what the change in the angle is, so we are looking for d theta dt. And we're looking for that at a specific value when x is 15. X is a variable, so we can't plug in yet. The searchlight being located 20 feet from the path, however, is fixed, so we were able to plug in that 20 right off the bat. Okay, we need a relationship between theta, x, and 20. Notice we have theta, we have opposite, and we have adjacent. So we should probably use tangent. So opposite over adjacent, x over 20, is equal to tangent of theta. Solving for x, we get that x is 20 tangent theta by multiplying by 20. Okay, so now we can take a derivative. Dx dt should be equal to, well, derivative of tangent is secant squared. So 20 times secant squared theta, and then times d theta dt by the chain rule. Okay, so then we can solve for d theta dt by dividing by secant. So we have d theta dt is equal to 1 over 20, but 1 over secant is cosine, so we can just make that cosine squared when we divide. Okay, now we want to plug in. We can plug in, so we can get 1 over 20 times cosine squared theta times 4, because we know dx dt is 4. So 4 over 20 is just 1 over 5, so that's 1 over 5 times cosine squared theta. But now we have a cosine squared theta. We don't know what theta is when x is 15. So we could do, we could plug in 15 over here and then do arctangent to cancel out tangent and give us theta. But another method is just to draw a triangle and just figure out what cosine is and plug that in directly. So if this is 20, and this is 15, and this is theta, then by the, we want to know what cosine is, so we want to know what adjacent over hypotenuse. So we need to know what the hypotenuse is. So we could use Pythagorean theorem. We square this guy, we square this guy, add them, take the square root. So it's the square root of 20 squared plus 15 squared. So that equals 25. Okay, so now we can do adjacent over hypotenuse. So this means that the cosine must be equal to 20 divided by 25, which is 4 over 5. Now that I know what cosine is, I can say that d theta dt is equal to 1/5 times 4 over 5 squared. So that's 16 over 125. So that's 0.128. And this is the rate of change of an angle. All of our trig values for angles are assumed to be in radians. So this is radians per second.